how changing the length of the string affected its resonant frequency. Sorry. So our independent variable is the length of the string, and the dependent is the resonant frequency.
Control variable, we felt like there were three main factors to control: the material or the density of the string, the tension of the string, and the diameter of the string. Firstly, for the material, we will only use strings made from the same type of material. We're thinking about maybe using nylon. For the tensile strength of the string, tension, we were thinking of using a pulley with set weight attached to it and keep that constant. And for the diameter of the string, we will also only use strings made from the same diameter.
Sounds good. Just out of interest, what do you use to measure the diameter of perhaps a string? Yeah, screw rate micrometer. Just the job, isn't it? Gentlemen.
So our question is how the frequency of the string will change depending on the cross-sectional area. We'll measure the diameter of the string and then use pi squared to work out cross-sectional area. The dependent variable will be the frequency produced, and we'll measure that with a microphone and audio analyzing software like Audacity.
Oh right, yeah.
That's one method.
Yeah.
Or also to just use an electric guitar and plug it into the grayscale scope.
Yep. So it's going to work nicely.
The control variables are the same material of the string and also the density of it. The length of the string, the tension on the string, the temperature, using the same way to plug the string every time. And also, since we'll be using new guitar strings, we need to make sure that we stretch the strings before using them, but we need to stretch them all by the same amount. And also use the same thickness of plectrum.
Yep. You've picked up on something. It's a guitarist's nightmare. The breaking of a string just before a concert. Because, you put a new string on, and you tune it up, and it promptly stretches, and you tune it some more, and it stretches again. And it keeps on doing that it can do it for 3 or 4 days before they settle down. So you've picked up on the idea of new string, in fact, may not be the easiest thing to deal with. As I say, they do stretch, in reality they do. And once you've got them stretched, they will stay reasonably well behaved for quite a long period of time. Just, can you look at these strings with me carefully? Particularly the metal ones, it's more obvious. Now, there's something you've picked up on that you have to keep the same. Now, will you look at those strings and can see that one of those precious things that you're going to measure and keep the same has got a slightly faulty bit?
It's rusted.
More than that.
I guess thinner in the middle.
Can you look very, very carefully at them? And you picked up on this thin bit.
Well, but where the thingies are, though.
Yep, where the frets are. They are actually not the same diameter.
Yes, they are.
Now, clearly, in your particular case, that's not going to be a consideration. But when you say you're going to measure the diameter of the string, can you be a bit more specific about how you're going to do it? Because you're all going to have to. You're either controlling it or you're changing it. So what would be crucial about the measurement of the diameter of the string?
Take an average of at least 3 points,
Yeah.
and not where the frets are.
Yeah, that's the clincher, isn't it? We need to have taken those measurements several times before we can be sure. It's particularly the case, I'll warn you, with wires. The way in which wires are made is by what's known as drawing them. And basically you grab it by the nose and pull. Now, that, generally speaking, does produce a nice round wire. But on occasion, it will produce something that's distinctly elliptical. So there you are, you measure your diameter, and that's it. And you do it a few more times, and then it's suddenly changed. And you look at it, of course, and what you've actually done is you've gone across the other axis. And that can be a problem. Okay? Just as a rounder-upper, I've got something else I want to show you on the board. So the dreadful truth, as it were. There we are. Those are the facts. Okay. So, the frequency expression can be put in the form, the bit at the bottom. Frequency is the root of the tension over the mass per unit length, right, divided by 2 times the length. So we've got string tension, we've got string mass, and we've got string length all involved in that. Now that looks fairly foul, but with your amazing mathematical abilities, I'm sure you can see that there is a way of turning that eventually into a y equals mx plus c sort of an idea. It would take a bit of rummaging around, wouldn't it? But as you pointed out right at the beginning, what we got to get at the end of all of this is a graph. And that graph's got to be a straight line with a slope that we can draw some conclusions from to show that what we did was making the difference. And because we've got that as a piece of theory, we can go back to it and again, as part of your conclusion, it says, are you drawing a conclusion that is reasonable with the data that you have processed? Now I'll just flip over to that. So look, here we are. Conclusion and evaluation. States a conclusion with justification based on a reasonable interpretation of the data. In other words, you're saying, this is what it does show. What do you think justification means? How would you justify your conclusion about anything?
You could state points or values from the graph itself, and then directly show the relationship with what you're saying about the thing in general.
True, very much true. How many of you have used Excel on a reasonably regular basis to plot graphs? Goody goody. In which case, are you aware of a thing that you can put on with your line of best fit?
Go through the origin.
Well, and hopefully it will go through the origin. But there's some facts that Excel will give you when you put on your line of best fit. Have you seen it?
You can put the equation of the line.
You can put the equation of the line, and there's one last little bit.
Error bars.
There are the error bars. Have you come across just a thing that says r squared?
Yeah.
Oh yeah.
What does it mean?
I haven't tried it yet. No.
Okay, well, it would be well worth you finding out about that. That's a piece I want you to go away and find for yourselves. Okay, I'm just pointing it out to you. But when it comes to your justification part, that might be very useful. Okay. You've mentioned error bars. What are you going to do with them? We have a graph. You draw a line of best fit. Is there anything else you can do with your graph? Why do we have the error bars there at all? Just for decoration?
Show the uncertainty. Show the uncertainty.
Show the uncertainty. So how could we make use of them?
If the line of best fit, if those all the point and until the ends of the error bars, as long as they lie in the line of best fit, then it's reasonable.
Yeah. Again, I want you to go away and do a little bit of research about what can be done. There's a very useful piece of stuff that you need to see. 2 minutes. There you are. This is the official IB organisation thing, and here it is. See what this person did. What is there on that graph?
3 lines of best fit.
3 lines of best fit. Well, only one of them is the line of best fit. One of them is the maximum slope, and one of the other one's the minimum slope. So they've really made use of their error bars, saying, okay, there's my line of best fit, and the answer lies somewhere in between these two extremes. Okay? Now, if we go back to draws a conclusion with justification, that's the sort of justification you're going to need. Alright? And that, as they say, is that. So, thank you very much. To be continued. Will you go away now and bring me a design now? Shall we say, got a week to go, when we come back from holiday? Would that be suitable? Okay. Go do it. Thank you very much.